A massive ship's main engine, it's just an incredible piece of engineering. We're talking about thousands of horsepower, enough to push these colossal vessels across entire oceans. It's basically a powerhouse of controlled explosions and just immense, immense heat. But deep inside all that heavy machinery, there's a hidden system, constantly working, constantly watching. So what's the one thing that stands between that perfectly running machine and just a catastrophic, molten failure in the middle of the ocean? What's the secret guardian angel keeping it all from going horribly wrong? Well, the answer, it's probably not what you're thinking. It's not another giant pump or some massive steel plate. Nope. It's a quiet, invisible, and incredibly precise little electrical signal. And trust me, understanding that signal is the key to the engine's survival. That signal has a name. It's called the 4 to 20 milliamp signal. Now I know, that sounds super technical, but it's actually a beautifully simple language that the engine uses to tell us exactly how it's feeling. Let's break it down. So, what is it really? Well, think of it like a universal translator for industrial machines. It's a standard way to send information. In our case, it's translating the very real, physical flow of cooling water into a number that the control system can actually understand. But why this type of signal? Why not use voltage? Well, an engine room is a really noisy place, electrically speaking. A voltage signal can get all kinds of distorted by that interference. But a current signal, it's way more robust. It can travel over really long cables without a problem, and as we're about to see, it has this brilliant, built-in safety feature. Okay, so how do we actually get from water, real water, sloshing through a pipe, to this neat little electrical number? The whole process is actually remarkably straightforward. It all starts with the cooling water just doing its job, flowing through the system. There's a device called a flow transmitter, and it's mounted right on the pipe. Its only purpose in life is to watch that water. It measures the flow, and then it acts like our translator, converting that physical rate into our 4 to 20 milliamp signal, which then travels down a wire to the engineers in the control room. And here's the magic of the whole system. There's no complex algorithm, no weird conversion table you have to memorize. The relationship between the water flow and the electrical signal is a perfect straight line. It's simple, it's reliable, and it's incredibly easy to understand. This table right here, it's basically the Rosetta Stone for the engine's cooling system. If there's zero flow, the signal is 4 milliamps. At maximum, 100% flow, it's 20 milliamps. And everything in between scales perfectly. 50% flow? Boom, 12 milliamps right in the middle. Once you get this chart, you can basically speak the engine's language. But look, this isn't just about checking if things are running efficiently. This signal is a critical alarm system. You could say its most important job is to tell us when things are about to go very, very wrong. So imagine you're the engineer. You're watching the monitor in the control room and you see that number start to creep downwards. What does that actually mean? What happens if that flow of vital cooling water starts to fail? Well, the system is designed to scream the answer at you. A value like 6 milliamps isn't just a number, it's a siren. This is the point where the whole system shouts, danger. It translates to a critically low flow of cooling water, and you better believe alarms are going to be sounding. And the danger is absolutely real. Without enough cooling water, temperatures just skyrocket. Cylinder liners overheat, pistons get damaged, and the entire engine is at risk of seizing up. In short, that little 6 milliamp signal is the very last line of defense before a truly catastrophic failure. Now, what about the other end of the scale? High flow, where the signal is getting close to 20 milliamps, is generally less of an immediate crisis than low flow, but it's not harmless. Over time, it can actually erode the piping and put a huge strain on the pumps, so it's still something you gotta watch closely. So let's put ourselves in the shoes of that engineer. You're in the engine control room, and these numbers on your screen, they're your eyes and ears inside that massive, roaring machine. This right here, this scenario is what it's all about. If you see a reading suddenly plummet from 15 milliamps, which is a healthy flow, all the way down to 6 milliamps, that is a crisis. You don't sit down and write a report, you act. You are moving, checking pumps, checking strainers, trying to find that blockage before the engine literally cooks itself. And this brings us to what I think is one of the most brilliant design features in this whole system. It's an idea called the Live Zero, and it's a simple concept that prevents deadly mistakes. The logic here is just genius. Think about it. If the system used 0 milliamps for zero flow, how would you know if the pump was just stopped or if a wire got cut somewhere? You couldn't tell the difference. By making 4 milliamps the signal for zero flow, a reading of 0 can only mean one thing. There's a fault in the system itself, like a broken wire. It's the difference between, hey, the pump is off, and, hey, I can no longer trust this instrument. It's a fantastic little failsafe. So, as we start to wrap this up, let's just zoom out for a second. This isn't just some number on a screen or a clever bit of wiring. This is, fundamentally, about survival. Just think, everything that gets hot inside that engine relies on the cooling water that this one little signal is monitoring. The cylinder liners, the pistons, even the lubricating oil and the exhaust valves, their health is directly 100% tied to the story being told by that 4 to 20 milliamp signal. I love this quote from the source material because it just hits the nail on the head. It's a powerful reminder to never, ever forget the physical reality behind the data. That number isn't some abstract concept. It represents real, life-giving water protecting a real running engine. At the end of the day, these instruments and signals, they aren't just accessories bolted onto the side of the engine. They are as vital as the pistons and the crankshaft. They are the nervous system of the machine. They are the engine's one and only lifeline. So, I'll leave you with this. The next time you see a simple number on a display, whether it's on a ship, at a factory, or even just on your car's dashboard, take a second to think, what physical reality does that number represent? What's the story that little number is trying to tell you?